Thank you.
Okay, good evening, everyone. And thanks to Professor Pradeep for organizing this meeting. And I'm hopeful that at the end of my talk, I'll get some collaborator. So the title of my talk is Biomolecular Simulations at Different Time and Length Scale. Oops. Yeah. So the research interest of my group lies mainly on two different areas. One is understanding the mechanism of action of various disease-causing proteins. And the second one is exploring the long-term stability of biomolecules using biocompatible ionic liquids at room temperature. So the general properties that we address mainly are the change in protein structure and dynamics upon ligand binding and also due to mutations in protein, ligand binding strength and specificity, and also under the second area, we look at DNA-IL, DNA protein-IL interactions. And our tools and resources are the following. Our primary tool is molecular dynamic simulations. And the resource we use for this particular area is to utilize the available experimental data. We use the data from an experiment. With that, we validate our simulations, and then we provide useful insights, what is not reachable by experiments. In cases where experimental data are not available, in such cases, we also do in vitro experiments. We'll give you some data on that as well. So if many of you would be familiar with the different time scale of molecular modeling, my group works mainly in the atomistic time scale, atomistic or nano to microsecond time scale by molecular dynamics. We also work at the interface of quantum and the classical, and that is called QMMM, quantum mechanical, molecular mechanical, hybrid quantum and classical. We also work on coarse graining, where we can go up to millisecond timescale phenomena to cover. In honor of Professor Pradeep, I would like to start with a chemistry project. So I do have mix of chemistry and biology, so I would start with a chemistry project, where my topic is nanostructural organizations in ionic liquid water binary solutions and its applications in biology. Ionic liquids, in the last month, there were a couple of talks. A quick glimpse, ionic liquids, as the name implies, composed of ions. The cation is organic always. Organic cations, like here I have imidazolium, you can have pyridinium and so on. And the anion could be acetate, PFs, could be inorganic, sometimes can also be organic. So these big cations and anions, the bulky cation and anion, they don't mix very well, and they form a frustrated crystal. And because of this frustration, in spite of being two strong ions, they make a liquid, and that's why they are called ionic liquids. So why to look at nanostructuring in IL water solutions? I don't know how to write that. Anyway, so why to look at the nanostructural, nanostructuring? Because all biological experiments are performed in IL water binary solutions, so therefore it's wise to look at IL water binary solutions rather than the neat IL. And this is also an experimental data where there is a very interesting observation what we got from 2012. In 2012, Stevanovic did the experiment. The density of ionic liquid, neat ionic liquid, is 1.05. And then when they added water, which is having a lower density, interestingly, the density increases. So this is an interesting observation that you are adding water, which is having lower density than IL, neat IL. In spite of adding water, your densities increases. So what is happening there? So that interests us to find out the microstructural organizations. So we took different composition of IL and water. This is a mole fraction of water, mole fraction of IL. Again, we checked the literature and we found this is not a general phenomenon. When my IL is acetate-based anion, then there's an increase, initial increase in density. and then the density decreases. But when the anions are others, BF4 or TFA, the density decreases monotonically as one expects. So what is happening? We carried out molecular dynamic simulations, and then what we found out is very interesting, is that we found anion water wires. So we have acetate ions. So you see here is one acetate, there is another acetate, in between there is a water molecule. So what we found is acetate water, acetate water, acetate water, a long wire of anion and water. And because of this wiring, due to the added water, the acetate, the anion molecules come closer. In the process, when anions come closer, it also pulls the cation. My cation was imidazolium, and now the imidazolium is stacking better. And not just that, we also see there is a hydrophobic tail, and the hydrophobic tail aggregation is also increasing. If you look at the peak intensity, as I increase the density from 0 to about 0.5, 0.7, the density or the structuring among the tails are also increasing. So what we basically found out that anion structuring induces structuring among the polar cation head groups, and structuring in the polar domain in turn induces structuring of the non-polar tail domain. And therefore, when you add low density water into IL, the binary mixture density increases. So we given that explanation. Then moving to the application of IL water. There are quite a few reports that proteins have enhanced stability in ionic liquid water binary solutions. And this is one example by Fujita et al. In 2005, where they found this is cytochrome C protein. The cytochrome C protein, if you increase the temperature at about 80 degrees in water as well as in buffer, the protein denatures. But in IL, red is one IL, blue is another IL, the protein cytochrome C remains quite stable even at high temperature. So, subsequently, there are quite a few studies that proteins really keep, ionic liquids in presence of water keeps protein stable for a long period. That encourages us to look at the DNA story. So we pose a question, can IL water solutions be used for greater stability of DNA and other nucleic acids? Nucleic acid samples are important in forensic sciences and also in biotechnology. However, DNA is not stable in aqueous solution at room temperature. So to start with, we thought we'd do MD simulation. So we did the MD simulation where in this box, if you look at the blue one is DNA, and DNA is hydrated in water, which are in red. We also added different concentration of ionic liquids, which are in green. Different IL concentration we used from dilute 0.2 to 28%, quite high, which is about 23 molar. And we also used different ILs, bemene chloride, bemene nitrate, bemene acetate. We also changed the cation from bemene to choline and so on and so forth. What we found is pretty interesting that apart from interacting with the phosphate backbone, the IL cations are also getting into the minor groove of the IL, of the DNA. We also checked the interactions. We found that particularly the IL cation, which is bemene here, bemene interacts with the phosphate backbone by electrostatic mainly. However, with the minor group and major group, bemene cation also interacts by both electrostatic and the van der Waals interactions. So this is something excites us to see whether IL molecules are really binding to the minor group all the time. Then we took different ILs, TMG acetate. So most of the ILs what we are using here are biocompatible. So this is the guanidinium based, this is choline based, and many of the ILs are synthesized in our lab now. So we found that different ILs, no matter what IL it is, the IL molecules get into the minor group and replaces the water. And this is the, making a long story short, that DNA do have a spine of hydration. DNA have a lot of water molecules in its minor group, and that is called spine of hydration. Here, the red is the water oxygen and white is the water hydrogen. So to start with, at 0 nanosecond of the MD simulation, there was a lot of water molecules in the minor group. As time passes, a lot of ionic liquids come in, and they slowly get into the minor group, replacing a lot of water from the minor group. If I show you this movie, that basically gives the whole story. So this is the DNA. We took DNA dodecama. This is the minor group where we have spine of hydration, a lot of water molecules, water chain. And these are IL molecules which are added into the solution. So if you now see solely, the one IL molecule comes in, IL cation particularly, then it gets into the minor group, pushes out a lot of water molecules. The second IL now trying to get in there, gets in, pushes more water molecule. And now we do have a IL cation water IL spine in the minor group. And so we propose that this partial dehydration of DNA by IL cation serves the basis of long-term DNA stability, as it prevents the hydrolytic reaction. So DNA gets hydrolyzed because of that spine of hydration. But now since IL molecule switches cation, getting into the minor group and basically reducing the phosphate-phosphate repulsion, now the DNA is stable at room temperature for a long period, and the bDNA conformation is also intact. So for this particular MD simulation, which is done in our lab for the first time, there was no experimental data in literature. So we had to do experiment ourselves. So this is the first in-house experiment where we did the CD spectroscopic analysis to see whether DNA returns its B conformation. And we found that irrespective of IL concentration, at all IL concentration, the DNA B conformation is intact. To confirm that it is the minor group binding, we then did fluorescent dye displacement assay. In this assay, basically DAPI and West, they're known minor group binders of DNA. So when DAPI and West bind to DNA minor group, they give 100% intensity. And when you add the IL concentration and increase the concentration, then you can see both DAPI in blue and West in red, both DAPI and West intensity decreases, which implies that IL molecules are indeed binding to the minor group. And so we propose that this minor group binding of IL is the mechanism of long-term DNA stability. We expanded the application of IL water binary mixture by taking different IL imimaceted.
Seemingly a network problem at IIT.
Not sure. I'm in the campus and it still looks connected.
Yeah, some campus has many wires going. And so Abhijit, are you there? Suraj, are you there?
Yes, sir, I'm here.
Okay. Glad to wait. Yeah, you are back. Okay, you may be muted, so you'll have to unmute and then start.
Yeah. Can you see my screen now?
Yeah, I'm sure.
So then we expanded the IL water binary solution application by storing DNA sample in different ILs, imimacetate, bimimacetate, choline, lactate, for 24 months now. And every 3 months, we basically take little sample and check whether my DNA is intact. And we are storing at room temperature. And as you can see, the DNA in water is completely denatured. There is no band here from the gel electrophoresis. Whereas in all ILs, you can see a strong band, particularly for 2080 solution of IL and water. So that means my DNA is intact. We also took the CD spectra, and DNA in water is this, which is completely denatured. DNA fresh CD spectra is this, and which is matching very well with our DNA IL water solution. So that means our IL water binary solution is keeping DNA intact for a long time. I'll skip this, and then So then moving to another project where we basically look at the drug, the disease-causing protein, which is HIV protease. There are a lot of reports that there is drug resistance mechanism of HIV protease mutants, and there is a need for irreversible inhibition. So this is a complex life cycle of HIV protease. I don't want to go to the details. This is the protease structure. What this protease does, basically, it cleaves this long polypeptide. Until it cleaves this long polypeptide into smaller chunk, the virus is not active. So therefore, there are 10 FDA-approved drugs which can inhibit the activity of this particular enzyme, HIV protease. Looking at the experimental data, these are different FDA-approved drugs, indinavir, nelfinavir, sacubitril/valsartan. They're different FDA-approved drugs, and they cause, the mutant of the protease. Here, different mutants are there. This is a wild-type protease. This is protease with active site mutation, protease with non-active site mutation, protease with active and non-active site mutations. So you can see, look at the bracket, the values in the bracket. So for the wild type, if it is 1-fold resistance, for active site mutant, it is about 10-fold. For non-active site, it is about 1,000-fold. And for active and non-active site mutant, the resistance is 10 to the power 3 to 4-fold resistance. So the question is how these mutants are basically causing the drug resistance. We found allostery. We did MD simulations, but the standard analysis could not fetch us any detailed information. So what we did, we basically did the network analysis. In the network analysis, what we do, we basically look at the signal processing among the different residues. So this is a complex network of HIV protease. I'll keep this simple. So what we found, this is a connection between some of the mutant residue to the flap of the protease. We found in the wild type, the residues which are mutated, they're closely connected to the flap. So the flaps basically, they act as a gate. The flaps open up to allow the drug get in, and then again, they have to open up to get the drug out. In case of non-active site mutant, which is a variant, you see that path became very corrugated and very long. And because of this long path, now there is no connection between the residues in the pocket, in the non-active site to the flap, and therefore now drug resistance is a regular phenomena in the mutant. Similar phenomena had happened in other cases of residues. We also found out, this is very interesting that, mutations, it causes drug resistance, but the HIV protease function remains intact, meaning the substrate can get in there and substrate gets cleaved. The polypeptide gets cleaved, only thing the drug is not affecting. How it happens, we found out that the substrates are usually long, and when it binds to the protease active site, it kind of clamps the two flaps. Here is a clamp, and because of the clamping, the protease flaps are closed, and therefore the activity of the protease is intact. Whereas the drug, which is here, this is small molecule, and this small molecule is not able to keep the flaps together, and therefore flaps open, and therefore the drug effluxes out. We calculated the loss in free energy of binding in the variant versus wild type, and we found that there's a loss of 12 to 71% in binding in the variant compared to wild type, and that trend matches very well with the experimental data, which shows 14 to 78-fold drug resistance for these FDA-approved drugs. So therefore, people are now looking at the irreversible inhibitors. For the irreversible inhibitors, they're testing epoxide-based inhibitors. EPNP is one such epoxide inhibitors. But problem is there is no reaction mechanism available. Neither the structures of transition states or intermediate are available. If we know the structure, transition state and intermediate, we can design drug, because most of the FDA-approved drugs, they're basically the intermediate mimic of the substrate. So here we are looking at the reaction in the active site of the protease, and therefore we have to opt for quantum calculations, because here we are having a reaction, so therefore electrons are involved, but we cannot do a full quantum calculation because protein is very large. So what you are doing.
So Sanjeev, 20 minutes are over, okay? So another 5 minutes to go.
Sure.
Yeah, thank you.
So what we are looking at, we are basically looking at the active side of the protein quantum mechanically, and rest of it by molecular mechanics. So we did quantum QMMM calculations, and from the QMMM calculation, we got the free energy profile. We found it is a SN2 reaction where there is a transition state, there's an intermediate, and there is a transition state 2. And we then looked at the structure of the transition state and intermediate, and we found that water is playing a very important role. And interesting thing is, many of the water molecules were not in the QM region. These water molecules were in the MM region. They get into the quantum mechanical region and supported the transition state stability or intermediate stability. You can see here the water molecules, they are in the hydrogen bonding distance, and they are stabilizing the oxyanion intermediate in this case. I'll skip there. So this is the reaction mechanism, what you propose. So this is the aspartate of the protease active site. Aspartate attacks the C7 by SN2 reaction. And then there's a transition state formation. Water is stabilizing the transition state. In the intermediate, the OC7 bond is formed. And the oxyanion intermediate is formed. Water stabilizes transition state where the proton from aspartate SPH transfers here, and the reaction takes place in two-step SN2. So those are examples I showed you by molecular dynamics and QMMM, but there are phenomena which happens in a larger time scale. Here is a case where I'll be talking about a protein called CETP, and this protein plays a very crucial role in cardiovascular diseases. How it works is basically, as many of you know, that HDL is a good cholesterol and LDL is a bad cholesterol. Why HDL is a good cholesterol? Because the HDL, extra cholesterol, goes to the liver and then it goes for excretion. Whereas the LDL, it gets deposited in the cholesterol pool, and therefore we get more and more fat. CETP plays an important role by balancing the HDL and LDL level. So what CETP does, CETP basically takes the lipids from HDL, and in the process it is reducing the HDL level and increasing the LDL level. So there's a continuous search to find out how CETP is basically reducing the HDL level and increasing the LDL level. Only in 2012, there was a cryo-EM study by which they found out this kind of structure where CETP is basically bridging between HDL and LDL. So based on this cryo-EM structure, they proposed this schematic diagram where this is HDL, this is LDL, and CETP is in between. So they proposed that there is a ternary complex formation, but they still could not say how the lipid is being transferred. We applied coarse grain simulation to model HDL. This is the HDL structure. We model LDL. We also model very large low density lipoproteins. So my HDL, LDL are modeled by coarse grain. We also model CETP, and now my HDL, CETP, LDL complex is formed. And now when you carried out the coarse grain MD simulation, so this is my HDL, right side is the LDL, and in between is the CETP. As you can see, these are the lipid molecules. Red is one kind of neutral lipid, and yellow is another kind of neutral lipid. As you can see, the CETP has a tunnel, and through the tunnel, it is basically getting the neutral lipid from HDL and transferring the neutral lipids to the LDL. So this microscopic information of lipid transfer mechanism we could brought out from coarse grain simulation, which was otherwise not possible from all atom simulation. Very recently, we are also working on dengue virus and Zika virus. I'll skip for this. Okay, so basically what we found out that, Zika can sustain high temperature, and we raised the temperature. We simulated, again, this is a coarse grain simulation. Zika at 40 degrees Celsius remains intact, but dengue at high temperature broke out. We also looked at the interfaces, and we found that a lot of hydrogen bonding and electrostatic interactions are lost in case of dengue, Whereas in case of Zika, the residues are such that hydrogen bonding and electrostatic interactions are maintained. And that explains why Zika is thermostable, but dengue is not. So that brings me to the conclusion that science at atomic and molecular level is very interesting, irrespective of the approach, theoretical, computational, or experimental. My knowledge is very limited into the atomic and molecular level, as I showed you. So we need to make a bridge among different scales through our expertise. And that's why Professor Pradeep is organizing this. So I hope that I'll get more inputs and collaborations in coming years to come. Please feel free to write to me or call at this number. And I would like to thank my group members. This is a long time old picture though. And thanks for your time.
Sanjeev, very nice. We have just about 4 minutes or 5 minutes or something for questions. So let me start by asking 1 or 2 questions and then leave the floor for others to ask. So you touched upon in the very first case, you were talking about water, ionic liquid water, linear chains.
That's right.
So now my question would be then, that the density changes and all that. So let me just focus my attention just to that. And that would suggest that this kind of a liquid at certain conditions, you may have extra ionic conductivity, or electrical transport could be very different in certain conditions. And that would mean that you can tune electrical transport. You have different directions coming out from that. So that is the one side of that problem. And that obviously means that if that ion, for example, if it were to be magnetic, then that is a magnetic order and then associated questions that you may think of. The second related thing is that when you are density changes, are you also saying that at some ionic liquid under certain conditions, you may have different phases of ionic liquids? I mean, I'm talking about solid state. And
yes.
So I would leave these 2 questions and then take your comments or suggestions on that. Thank you.
Thank you. So yeah, conductivity is something very important, and people are working on. Professor Ramaprabhu in physics department, he was working on battery where he was using ionic liquids. So we also have done calculations of the conductivity, and there also we found that conductivity increases for certain ions when you add little amount of water molecules. So for ions, the conductivity is pretty high. But it gets even better if you add certain amount of IL to certain ILs, not all of them, not a general phenomenon. And your second question
on phase.
Yes, yeah. So we kept changing the water concentration, and we found that up to 50%. Again, it varies from IL to IN because the anion and cation, their structure matters a lot. For certain ILs, what we have studied, so there we have found that up to 50% of 58% of IL, the IL nature is intact, meaning their conductivity, their density is very much intact. But beyond that, then water takes over. Then water characteristics prevail. We also have done some phase studies for water oil microemulsion. So there in water oil microemulsions, we added IL, additive amount. And then there we found that the water oil microemulsions, which was stable up to certain water content, that gets much higher with the addition of additive amount of IL concentration. So yeah, you are right.
Thank you. Thank you. Let's Hemachandra.
Yeah, thank you, Professor Pradeep. Great talk, Professor Sanjeev. One small quick question. So you have done this stability assays on double-stranded DNA, right? So I'm more curious because single-stranded DNA is much more prone to hydrolysis. The stability is much lower. So did you test your stability of single-stranded DNA in presence of ionic liquids?
That's our ongoing research. We are still not very successful. Right now, we are basically working on the plasmid DNA because that is useful for biotechnology. We're also working on the RNA.
Okay.
Still no success, but we are still trying.
Oh, just to add on to that, so generally in case of proteins and other, so we see salting out effect, right? When you increase the salt concentrations, do we also see such effect in presence of ionic lipids, or because generally ionic lipids stabilize the structures, but if we compare it with the normal proteins like KCl and other proteins, there is a salting out effect. So do we see that at a higher concentrations?
So, why we did not go for protein IL that's a very complex story. So salting out is there in some proteins, not for other proteins. So since proteins outer surface varies from one protein to another, depending on their hydrophobic, hydrophilic residues. So for proteins, there is no general rule that this IL will stabilize and there will be no salting out.
Right.
It's a random phenomenon for protein.
Right.
But for DNA, so far, we have found that irrespective of IL we take, we checked calf thymus DNA, we checked salmon sperm DNA, and we found that DNA is quite stable at
double standard, right?
Yes, double standard. Yes. Yeah.
Okay. Yeah.
Thank you.
Yeah,
and
thank you.
I don't see any other question. In case you have a question, please shoot. Otherwise, we will move to Sridhar now.
Thank you.
Chaitanya, you have a question.
Yeah, so Sanjeev, very nice talk. I just have a small question. So regarding your QMMM calculations, so you said that these water molecules are coming from the MM region to the QM region, right? In order to stabilize the complex. So, so how much this energetical changes you are seeing there? So in general, like when you add 2-3 molecules of water, quantum mechanical water molecules, I have at least observed that you can change by like 2 kilocalorie per mole to 3 kilocalorie per mole easily.
You're right.
Yeah.
If you look at this particular picture here, I did not talk about it actually. You can see in the intermediate state, we are getting about -3 kilocalorie per mole, stability. And that's because we have about 5 water molecules. You can see here 1 to 5. We kept only one water molecule in the QM region because from the HIV protease history, there was 1 water molecule, but 4 other water molecules came into the QM region. And taken together, this 5 water molecules is giving as high as -30 kilocalorie per mole stability to the intermediate. To the transition states also, it is giving quite a bit of stability.
So these MM, like whenever the water molecule is coming from the MM region, so you automatically consider as a quantum mechanical one, or you will leave that as it is? Like as
no. So these water molecules, that's why I said they're playing a co-catalytic role. They are not involved in the reaction. What they're doing, they're basically hydrogen bonding with the intermediate or the transition state, but there is no proton transfer from this water, or there is no proton transfer through water mediated. And that calculation also you have done here. If you look at the bottom one, you see when it is water mediated reaction, there is a barrier. So it is not water mediated, neither the proton comes from water. The proton comes from the other aspartic
Okay,
acid.
Sanjeev, let us move on. Let's move on. Yeah, thank you. And let's take the next speaker. I'm just sort of making sure that we close this at 8:10 or something.
Sure, yeah.
Okay. Yeah. Sridhar.
Good evening, and I'll be able to share my screen, right?
Yeah, of course. Yeah, it's not yet full screen though.
Yeah. Are you able to see the full screen now?
Yeah, absolutely.
Good evening, and thanks to Professor Pradeep for arranging this series of talks, and also to his colleagues who have been very persistent and methodical in following up and fixing the date and time. I think it was Suraj who was in email correspondence with me. Thanks to him for follow-up. I'm Sridhar. I work in the Department of Chemical Engineering, and I'm also associated with the Robert Bosch Center for Data Science and AI. So I structured this talk in 2 parts. In the first part, I'm going to talk about how you can do certain experiment design on networks and to identify leaks. And the prototypical network that we're going to look at is a water distribution network, which is an engineered system for which all of us are familiar with, having been consumers of water and so on. In the second part, I will show you how the problem lends itself nicely to an interesting graph theoretic problem. And that's where I thought I'll bring the theory and the experimental parts together. And this is also an inversion of how it was carried out. Initially, we came up with the theory first, the algorithms and the theory first, and then the experimental validation subsequently. I also would like to caveat, I'm largely a theoretician, and it's only the last 5 or 6 years, thanks to interaction with several of our colleagues here, that I started to do a lot of experiments and field validation, demonstration, and water networks. Just a quick the cartoon picture of a water distribution network. Basically, it's in the very important infrastructure, as we all are consumers of water. It transports treated water from source through a series of tanks, pipes, valves, and eventually to an end consumer, for instance, like an apartment, or as far as Chennai Corporation is concerned, an end node could be the entire campus itself. So this represents this cartoon figure. And depending on the level of granularity, whether you want to model right up to every house, or whether you would like to model every street, or like, as I said, in Chennai, if Chennai Corporation is trying to model it, they might be interested in agglomerating the entire campus as an end node. So this network representation is very useful representation for a water network. So our work on water networks has been, initially it was largely theoretical, in coming up with theoretical formulations, methods, and verifying it on using computer programs. So I looked at design of sensor networks for where should you place measurement sensors, flow sensors, how do you operate these networks optimally. Then, as I said, they came up with the theory for leak detection in poorly instrumented networks. And over the last several years, we've been doing some experimental validation. We have built, I'll show you some more detailed close-up photographs of the water network that we have built in the lab. And again, the last 3 or 4 years, we have also done some field demonstrations, including in the IT Madras campus, and as part of a DST project along with IT Bombay in Palghar district in north of Mumbai. So, I mean, this is again, we don't have to belabor the point, but there's a significant loss of water during distribution, and the amount of water lost ranges from very as low as 10% in certain places to as high as 40 to 50% in many Indian cities. Water network operators like to refer to this as non-revenue water. Basically, it's the water amount that you charge for minus, or the other amount that you pay for minus what you recover. As far as network operator is concerned, it consists of both real loss and apparent loss. Apart from being a social, having social implication in terms of loss of resource, it's also less energy efficient because you have spent a lot of energy in transporting a certain amount of water, but only a certain far less amount reaches the end consumer. So there's a loss of energy also, and because of leaks, there is always a possibility of infiltration and reduction in water quality. So what are the challenges? Majority of the pipelines are buried underground. They are, the pipe network is largely old. These are large infrastructure projects which are expected to last 50, 60 years. And most water networks have very limited instrumentation. And therefore, if you were to think of it as a chemical engineer working on process control, we are more familiar with, we expect to see a well-instrumented plant. However, a water network is not as well instrumented, and therefore this places significant limitations on what we can do with both data and with sensors. So there are several methods. Conventional methods include, these are possibly better for a limited, very smaller area. You can have visual inspection, acoustic methods, ground penetrating radar, or tracer gas injection. These might be useful once you have narrowed down the leak to a certain street or a locality. Then these kinds of methods could be used to identify the exact location of the network. Now, there have also been methods which combine a model and data. So where you use a model to predict what would be the flows and pressures in different parts of the network. And then if there is a mismatch, then you attribute it to a leak, and then you have certain hypotheses and use statistical and computational methods to identify the source of the leak. This, however, requires a well-calibrated network model and a large number of measurements. And also sound funny, but large network operators may not even have a detailed map of the network. Forget about having a well-calibrated hydraulic model. With a lot of data being available, purely data-driven approaches have also come up. But however, it requires a large amount of data, and most importantly, these are what's called supervised learning, where you need labeled data for both leaky and non-leaky situations. So you have collected data during good times when there are no leaks, and during bad times when there are leaks, and then you do some classification or pattern recognition methods to decide where your current data lies, whether it's in a leaky set or non-leaky set. What we are going to propose is a data-driven approach. It requires network topology is the only thing that is required, and certain balances across volumes. So let's start with a very simple, intuitive, and very simple cartoon figure again of the network. And this is very intuitive. And at the end of this, you might argue, oh, this is all very intuitive and commonsensical. And then I'll show you how we can generalize this idea to larger networks. So let's say that there's a network of pipes and nodes over here, and an inward directed arrow means 100 units of water is being supplied over here, and an outward arrow means 20, in this case 20 is coming out. So if you do a balance, there's 100 coming in, and say 50, 70, 80, and 90 is being consumed. So you know there is a loss of 10 somewhere. So 100 of units of water is being supplied in, and only 90 is being consumed. So there is a loss somewhere. So how do you identify? It's somewhere in this network, and one suggestion could be to go and measure every pipe in this case, and then find out where is the real leak. But that would be prohibitively expensive in a very large network. So one suggestion, what we say is, we partition the network, and what we do is that there are two ways you can do it. You can either place a sensor over here, or you could have, if there is a valve on this, it's usually water networks have isolation valves. So if you have a valve over here, you cut off this part of the network from the left part of the network from the right part of the network. So now if you do a balance over here, you see that 50 units is coming in and 40 is going out. So you know that leak has to be here. Leak is definitely here. There could be a leak in this part of the network also, but definitely we know there is a leak over here. So if you're interested in identifying at least one leak, let's say you take a very step-by-step approach and say, okay, I'm going to identify as many leaks as I can. So you know there's a leak in this part of the network. So then you go around and then say, I'm going to now, isolate E3 and E2. And then you see that 20 is coming in and only 10 is going out. So leak is somewhere in this, there's some leak, either in D1 or in the pipe over here. Right? So you have pretty much using a smart series of interventions by cutting off certain pipes using valves. You're able to isolate the root cause of the leak to a certain subset of the original network. And having done this, then you can use the conventional methods to identify the root cause of the leak. So certain assumptions, the network topology is known. That is, you know which nodes are connected to what and in what order. You are able to measure all the supply and the consumption with errors if necessary. If they could have random errors, and there are enough number of isolation valves present in the system. And the last measure is it's not a very significant, none of the last assumption over here is not a very significant limitation, and it can be relaxed. It just says that, I just introduced it to make the development and the theoretical explanation easier, that the leak is present only in the nodes and only in one node, but we don't know which node it is present in. Or it could also be in, a pipe. The point is it's only, both can be handled. So if you notice this, there is a systematic method in which this has been done. So what it does, I'll come to this algorithm maybe towards the end. So then I'll show you how this was, okay, maybe I'll say, spend some time on the algorithm. So you know there is based on initial set of measurements, you assume there is a leak. What you do is you partition it into a smaller network, and then you isolate using pipes or valve closures, do a repeated volume balance, and then I impute the leak to one of the two partitions. And as long as you're able to reduce the size of your network below a certain threshold, you keep repeating this until you have identified or isolated the leak to a network of a small enough size that you can go and then manually intervene and identify the root cause. And also I'd like to point out that in the manner in which most networks are operated in the Indian context, which is called intermittent operation, where water is supplied for a certain amount of time, you really don't need to measure flows, but you can do work with volume balances alone. So that's what makes it very attractive in the, especially in the Indian context. And in our discussions with some practicing engineers, they have found this to be an attractive approach. And in fact, this problem was suggested by by some of our colleagues from an engineering company. And therefore, this has a practical and local relevance. And that's, we were very excited that we could come up with a nice theoretical method and followed by experimental validation of this approach. So this is, again, we have in our lab, we have set up a fairly complex and I would say fairly one of its kind water distribution demonstration network. So it has an overhead tank of around 600 liters over here, and there are 4 overhead tanks of around 100 liters, and all the pipe fittings are of ½ inch, 3/4 inch, 1/4 inch. The advantage is the footprint is significantly lower. There are lab scale water networks in many places, but however they use much larger pipe sizes or valve and so on. Therefore, the footprint is larger, and that restricts the complexity of your laboratory validation. And another thing is this is completely modular, so it's almost like a Lego toy when you can plug and play, interconnect networks, destroy, and introduce all kinds of interesting possibilities. It opens your lots of interesting experiment and possibilities. This is another view of this. So a typical sub network would have a flow meter, a valve, an inlet valve, and each of this. A demand node is basically a tank for which water is supplied. There are valves leading into it and leading out of it. And this topology as what are the interconnection is completely as modular. You could disconnect, connect, and come up with your own network topologies. And all data is interfaced and collected and logged. Another close-up photo of the entire network over here. This one shows a valve which is leading into one of these tanks, and this is the control panel that is written in LabVIEW to collect and interface data. So very simple experiment where this is one source, the overhead tank over here, and D1, D2, D3, and D4 are basically 4 demand points, and T1, T2, T3 are intermediate nodes. So if you want to think of it, D2, D1, D2, D3, and D4 are basically tanks into which water is being collected, and they have level sensors, so you can measure the amount of water which is coming in. You don't necessarily need to know the flow rate through the pipes, because you're able to, what we'll show is we are able to estimate the flow rate by monitoring the level through a change in level in the tanks. So you monitor the level over here over a certain amount of time, and then you use that to infer how much water volume has been supplied. Unlike conventional methods, you can do a volume balance is good enough rather than having to precisely measure flows, which might be challenging. So in this case, we have deliberately introduced a leak in this node by connecting a pipe and a valve and opening it out. So there is a leak. So over 3 minutes, we recorded how much water was supplied through the source over 7.2 liters. And if you added up how much water was collected in the tanks D1, D2, D3, and D4, it was around 6 liters. So it's this kind of a mismatch cannot be attributed to pure sensor error alone, and therefore we expect there is a leak. But we really, at this point, even though it's like a game that I'm playing now, I have simulated the leak, but I'd like to ask you to imagine that you don't know where the leak is. So what you would do, we would do is you will first try and isolate. There could be many approaches to it. This is one of the approaches. You isolate this part of the network from this. So you put a valve over here and isolate this part of the network. So the amount of water supplied is 4.62 liters and delivered is 4.58. That is the amount of water collected in D1 and D2 for approximately 3 minutes. So this difference is marginal, and therefore you can assume that it is only the difference in this case can be attributed purely to measurement error. So you know for sure that the leak does not exist in either T1 or the pipes going to D1 or D2. So it has to be in the left part of the network over here. So then we go and then isolate this part. I put a valve over here and isolate the connection between T2 and T3. Again, the amount of water supplied is almost the same. So we know the leak is not in any of this shade in this dotted part of the network. And to finally confirm our suspicions that the leak would have to be in between T3 and D3 or in T3, we isolate D3, the tank D3, and then again there's a significant mismatch. So you know the source of the leak has to be in T3, and that's where you're so using a certain set of isolations, in this case valve closures. It could also have been by the measurements. If you are able to measure flows, you could have a similar situation could have arisen, but except that measuring flows in underground pipes is much more challenging. So closures of valves is an easier task, relatively speaking. So this is for a small enough network where, let's say that the difference between supply and consumed is around 10% at least. So, any differences can be attributed to a leak. Now, when you go to a larger network, given the sensor resolution and the difference, in this case, the leak was introduced over here with the pipe connecting 30 and 6. And as you can see visually, there is a significant amount of water that is being lost. But given the small flow rates in all these pipes, if you did a volume balance alone based on how much volume was supplied and how much water was consumed, the difference was less than 1%. And therefore, just pure volume balance, it was not enough just to look at, you need to have a proper rigorous statistical, you need to have a statistical test to come up with a decision on to determine the leak. So we used a one-sided hypothesis test. In those are familiar with statistical testing, this is the null hypothesis where there is no leak, whatever is coming in is equal to out, and therefore if you expect this difference to be a normally distributed random variable. So we have some idea of the statistics of this so-called residual. So all you need to bother about is what is coming in and what is going out. And you see whether the residual crosses a certain threshold, and if the residual crosses indeed a certain threshold, then there is a leak. And to avoid false positives or other kinds of things, we know that it's very unlikely that you will be able to, you will consume more than what you supplied. So we use a one-sided hypothesis in this case. It makes physical sense because it's unlikely that, it's impossible that you will end up consuming more than what you supplied. So you do a set of partitions similar to what I showed over here. And then in the first partition, there was the residual did not cross the threshold. The residual did cross the threshold, and therefore there was a leak. Second partition, the residual crossed the threshold. And these are the threshold values, and these are the observed values over here. And third partition, the residual again did not cross the threshold, so there's no leak. And finally, in about 5 experiments, 5 different set of experiments, we are able to isolate the leak. The original network is fairly complex. So again, let me go back over here. There are 32 nodes because, and the leaks could have in any of these 32 nodes. So it's like looking for a needle in a haystack. So rather than looking, this is a systematic way of identifying the needle in the so-called haystack by using, rather than trying and going and putting sensors everywhere. What we have shown is if you are able to monitor a certain, do certain interventions in a systematic manner, you are able to isolate the leak. So now, how do you generalize this to larger networks? What is really the trick that is going on? So this is, let's say, a cartoon figure of a larger network, and let's say that you first so-called partition the network into 2 parts. So when I say partition, which means you are basically using these red-colored edges, and I'm putting valves at closing using these edges to divide the network into 2 parts. So either in the network consisting of the blue-colored nodes and the green-colored nodes. So what I've done is I've put valves over here, and it has cut off this part of the network from the right and the left. And then I do a volume balance. If there is a leak in the left part of the network, then I go and then if I did a volume balance and I attributed the leak to the left part of the network, then what I would do is I'd go and partition the left part of the network even further. And then I would come up with these yellowish, orangish colored edges where I would use this to partition it. If on the other hand, the leaks had been identified in the right part of the network, then I would use these different edges over here, and then use this to further partition the network into sub-partitions. And you can see roughly, you would expect that with every such partition, you should expect a halving of the network size and so on. So the advantage is that you can store this is like a decision tree which you can compute up a priori and store it, which means that if you think there's a leak, the first thing that you need to do is go and then cut these pipes. So cut these pipes or isolate these pipes. And likewise, if the leak and then store again the next set of, in the next hierarchical process, you would store either this pipe, this pipe, this pipe, or the other 3 pipes over here. So you store all of these as in a decision tree, and then depending on where you attributed, where you found the leak, you keep repeating you keep marching forward and doing a set of experiments. So all of this can be done once and then stored as an offline tree. And then in practice, depending on what you observe, you go and make these sets of interventions. So how do we, in the very small, in the networks that we showed you, which we worked with experimentally, some of these could be done by visual inspection, right? But when you have a very large network, even this, for instance, it's not obvious.
You used about 21 minutes. Okay, no, yeah, thank you.
Yeah, so I'll be wrapping up in 2 or 3 minutes. So even a large network, visual inspection will not be able to tell you what exactly you need to do. So what this, as I said, this is a complete inversion of the process in which we came up with this. We first came up with the theoretical method, and then a couple of years later on verified this in the experimental facility. But I thought I'll motivate you and convince you with hard data from the network before going into net graph theory and net graph partitioning. So this is basically a problem in graph theory where complex networks, people will also recognize this. This is a problem when you want to partition the network into 2 parts, and roughly you want the 2 partitions to be of more or less the same size, because you expect, the halving of with each intervention, you would expect the network to get halved in size. And you also want to keep the number of edges that you are using to partition it, that you want to keep it that to a minimum. So you can do this math, you can pose this as a mathematical problem by first defining what's called the incidence matrix, which tells you which edge is connected to which edge, and the plus and minus ones are completely arbitrary over here. And then you define x as a vector for every edge, and x equal to 1 means that it's assigned to one partition, and x equal to 0 means it is assigned to another partition. So the objective is to minimize the cut size, that is a number of edges that you're using over here to cut the partition, and to ensure that the both partitions are of the same size. So this is a combinatorial problem which can be solved exactly for reasonably moderate size networks. We have also come up with an approximate solution. This is where the connection between between network science and graph partitioning comes in, where you find out the eigenvector corresponding to the Laplacian of the graph, and then the Fielder eigenvector, that is eigenvector corresponding to the second smallest eigenvalue of the Laplacian, and then whichever is positive, assign it to one partition, whichever is negative, assign it to another partition. This is an approximate solution, and with some experiments, we've shown that the answers are good enough. So this is, for instance, another example of a large size network, where in this case, rather than the leak being in a node, it is in a pipe. This is again complete simulation exercise, not a practical demonstration. So these are, water network people come up with challenge problems with the challenge networks. So let's say the network leak was in this pipe, but we didn't know about it. Again, it's a game like a game being played, a challenge game. The first stage, I would isolate these pipes over here, which are shown in black. And the next stage, and then I would do a volume balance on either the left or the right, and then I would attribute the leak to one of these sizes over here. Then I would in the next round, I would cut these pipes and then isolate the leak to this part of the network, and eventually isolate it to the offending edge. So we ran a lot of these simulations and on large-ish size networks, and then so our simulation results show that large networks require either, when I say 3% measurements, either you need to measure around 3% of the pipes. Remember, all that thing out, when I say partitioning, it could either mean actually putting a sensor there and measuring the flow, or cutting it off. So in this case, a large network with around nearly 2,000 edges, you don't need to measure all the 2,000 edges. You need to measure only roughly around 3 to 5% on an average flows of this, or isolate those many valves. So the bottom line is approximate solutions are also good enough as opposed to solving the problem exactly. Some of these are of course still challenges in terms of how to handle measurement error. So one of those in lab network, we were able to demonstrate that using rigorous hypothesis testing and statistics, you could distinguish measurement error from leaks. We used only network models and overall flows. If you had pressure measurements, how do you incorporate pressure measurements? And it would need a more rigorous hydraulic and mathematical model. Multiple leaks, you have to repeat the process. then if you really have optimal or minimal sensors for regular monitoring, then where should you place and to what extent can you isolate leaks? Although I talked only about leaks, and in physical networks over here, our feeling is some of these are generalizable to other kinds of network problems. Sanjeev presented some, my interest got piqued when he talked about networks, and so on, protein networks, I believe. So if you have chemical reaction networks or metabolic networks or other kinds of biological networks, can we use some of these ideas again? In some edges could mean relationships, or edges could mean something else. Nodes could mean, depending on the context. If you are able to cut off part of the network or measure certain edges, then can you use these to identify certain other properties of the network or certain irregularities that you observe in the network. So with this, I'll stop, and that's also my alarm that went on. And all the experimental demonstration was thanks to Prasanna, who graduated last year. And the theory was worked out by Arvind, was a BTech student. So now I think close to finishing his PhD at Washington. And my colleagues on this are Shankar Narasimhan and Murthy, Ramkrishna, and Mr. Murli, and so on. Acknowledgement is this was largely funded by DST as part of the Water Technology Initiative, and thanks to supplementary funding from IIT Madras, the Robert Bosch Center. And thanks again to all of you, and especially Professor Pradeep and his colleagues. And yeah, thanks. And I hope.
Thank you. Very nice presentation. And also on a very important socially relevant problem. And if these inputs can be incorporated right at the design stage itself, many of our problems can be solved. Let me ask you one question and then move on. So one of the problems India faces is, in addition to leakage, sewage entering the lines, right? Sewage entering the pipelines. So when you look at a problem of that kind, how do you address that? Or this very same network or isolation will work?
Yeah, in fact, as I said, this is what I also mentioned. Leaks result in, as I said, sewage entering the pipelines. So if you're able to isolate the leaks, then you can cut down the problem of sewage entry. If the question is, can you detect sewage entry? Then you need, if the question is about, can you detect sewage entry, then if you have some concentration measurements or quality samples, then we'll have to see how to bring that information in to isolate or determine where the leak is. So right now we have not looked at quality. Yeah. But quality is a downstream of quality deterioration is downstream of leaks. But if you can measure quality, will it help to know where the leak is? Yes, that's an interesting question. I don't know if that was a question, but definitely it can be used. Any extra information is always useful.
So when it comes to gas line leakages, is a similar, how do you do such measurements? Because the volume is not measurable in this case.
So gas line, in fact, Shankar and Murthy have worked on gas leak detection in pipelines, where you use both flow pressures, largely pressures, and a mathematical model of the system to be able to, and statistical tests to determine where the leak is. And in the case of a citywide gas distribution network, the problem becomes much more complex. But in large pipelines, cross-country pipelines, they actually tried this and implemented it as one of the cross-country pipelines, where they were able to, where they physically simulated a leak, and then using available measurements in terms of pressures and certain flows, because in gas pipelines also, because these are a lot of money, so there is both an there's a lot of incentive for both the supplier and the consumer to put up flow meters and so on, and therefore with both these and pressure sensors, they were able to isolate the leaks and determine which section of the pipeline it was in, up to a few meters, if I remember right.
Well, are there other questions?
I'll just also add, gas is slightly more challenging because gas flow is compressible. Here, water flow is not, we don't assume compressibility. So gas flow is also much more challenging in that sense.
Is there any from a sort of another interest, like our countries, the developing countries, where do you have lowest leakage? And is this because of better control of the networks? Or is it because of this better social awareness? Or
Sorry.
So among our kind of countries,
Okay.
you talked about several several cities here where
Yeah.
leakages are noted here. So if I take, let us say, east of the Asia and take these developing countries here versus Vietnam versus Cambodia or places like that, where the leak is less, is it because of a better social awareness or better billing mechanisms, or what is it?
I would think it's a combination of all infrastructure, social awareness, and combination of both technical, social, and of course political factors have to come together. Because water, you need to be able to bill water, you need to know how much meter water, and so on. There are all challenges are multifold. I mean, so if somebody is able to solve it, it's basically they've addressed all the issues: social, technical. For instance, one of the biggest challenges, and especially in Indian context, is faulty meters not working after a while. So, what do you do with that? So we are working on other ways of trying to infer consumption and so on. So, about technical, social, and political issues over here. Yeah.
Okay, colleagues.
Politically, because.
Let's take other questions if there are. So let me just continue on this and then ask the last question probably. The Robert Bosch Center in this network identification and related problems, is it that we are planning to have a national depository of all these data? And is it possible for us to come up with solutions if people face challenges? What is the direction?
Yes, so Robert Bosch Center is looking at several aspects. So one of the things is also collecting data. One of the proposals that we are working with Robert Bosch Center is data collection. And there are other groups also they are funded in just data collection, which will eventually be thrown open to everybody.
So in the context of these water leakages and water networks, there will be a national depository of that data?
Well, not, I mean, so right now we are looking at, of course, the data collection exercise that we are going to work with personally is at a very small level. So it won't be at a national level, but there are other groups who will be working on other kinds of systems, for instance, air quality and so on. Their data might also eventually become public.
Thank you. Thank you. Next speaker is Sumesh. While he is setting it up, I would like to tell you that this is an initiative to connect experiments and theory to have better interaction across the institution, identify new problems. And so I would like you to also throw open how you can possibly connect with others, how your expertise can be useful for others. Those of you who have already, in case you are interested in giving a talk in this series, please do write a mail and also indicate a possible slot. We generally do this on the third week of every month, third Saturday of every month. All right, Sumesh.
Okay, yeah, first of all, thank you for this opportunity. I think, this is a nice place for people to share the work and so on. So I'm planning to talk about some aspects of work that we do in the lab. So I'm primarily a computational person. And yeah, so I'll just talk about two little pieces, and considering the audience, I'll try to keep it as general as I can. So I'm going to talk about hydrodynamics of active particles in microchannels, and I'll explain this as I go along. So, okay. So this slide is essentially to illustrate what the system we are looking at. So Sanjeev gave talk on, looking at things on a molecular scale, while Sridhar was talking about things on a much larger scale. This is somewhere in between, things which might be difficult to see with naked eye, but you still don't need to go to, look at things on an atomic level. So the first picture that you're seeing on the left-hand side, so this is, inside the cell, if you look at, you always see filamental kind of structures, right? So what this particular experiment shows is that if you take out those networks and make a suspension of it, and this is how it would look like. So here the motion that you're seeing is not because of thermal fluctuations. It's not Brownian motion. It's the fact that there are ATP molecules present, and the chemical reaction mediated by these ATP would be translated into some sort of a mechanical motion. So these filaments are continuously moving because there is a continuous chemical energy that's available to them. And you can see that so this is present in a fluid, and the entire motion looks very chaotic or turbulent in nature. So we call this kind of a fluid as an active fluid. And the reason we call it active is because, typically to move a fluid, you need to push it, you need to apply some pressure or a pressure gradient. So unlike such fluids, here the fluid is moving because each of the constituent itself is a living entity, meaning that it can move by itself. So such a particle is what is called an active particle, and a suspension of such active particles is called an active fluid. So why is one interested in looking at such a fluid? So one possibility is what you're seeing on the second video here. So here, the background fluid is not exactly the cellular extracts, but this is a suspension of bacteria itself. Okay, so you have put this bacteria into a fluid. Each of them is moving, but this is a very dense suspension. And therefore, it's not about one of the moving, but you actually start seeing a collective motion of bacteria, like just like a flock of birds that you see in the skies. So what that means is that it's not just these particle or bacteria, but the entire fluid starts moving. And as a result of it, these gears, which are actually few microns in size, also start moving. So the question is, could you actually use these, to make micro machines and so on? So these are one example of why one studies the physics of active fluids. On the right top, what you're seeing is a image of spermatozoa cells in a reproductive tract. Okay. And what you see is that so here again, the sperm cells can be think about as active particles because they move by themselves, they move in a fluid, and in this particular case, they have to move in a very, take a tortuous path, and during its path it will come and it will encounter other cells, it will encounter debris of other cells and so on. So this is again an example of an active system. And the fourth one where you see the movie is a synthetic active system. So the three other ones I spoke about are all of biological nature. Here what you're seeing is this black particles are Janus particles, and they basically undergo certain chemical reaction which will make it move when there is light shined on the system. Otherwise, all it basically just behaves like a dead particle, and all the white particles that you have around are all passive particles which are just executing Brownian motion. So what you're seeing here is that the moment the light is on, you start seeing clustering of those passive particles around the active particles. So certainly interesting things happen, and the question is, how do you explain such systems? How do you explain the behavior without getting into biology, but based on more like a physical picture? So this is the kind of work that typically we are interested in. So okay. So I'll come to the first part of the talk. So that is where I'm going to look at hydrodynamic collision between a swimmer and a passive particle. So first I'll explain the system and maybe then I'll explain what happens. So we consider a simple system. So here you have this red particle. You can imagine this is essentially a swimmer, like one of those active particles that I spoke about. And then let's say that is moving from left to right. So it's a model system we are considering, and this is in a channel. Okay, so that black line show that it's confined in a channel and it's coming from left to right. And on its path, it actually encounters a blue particle, which is a dead particle. So you can imagine that suppose you are walking from left to right, and then there is an obstruction, and what you would do as an active particle. So instead of that, if it is a bacteria or a cell that's moving from left to right, okay, then if it sees a particle like this, what is the consequence that you are going to have? So that's the question being asked. And the difference between when you walk and a cell that moves is that when you are walking, the fluid around you is air, and the motion of air is not really going to affect you, your motion. But in this case, the fluid that is present typically is a very viscous fluid, and therefore when this red particle moves to the left, it generates a flow which will be seen by the blue particle, and the blue particle will disturb a flow which would be seen by the red particle. In other words, there will be an interaction between red and the blue particle. Okay, so this is typically a case when you have cells that will move and it will encounter some other colloidal particles or cells on its way. So just to illustrate what this happens, again here I have a movie. So this red is your active particle. So you can see that I have neglected all the complications associated with its body and move, deformation and so on. I am just saying that the whole thing is just a spherical object, and then this white is a passive or a dead object, and the vectors that you are seeing, all these arrows are going to represent how is the fluid velocity is. Okay, and the color blue is essentially indicating that the velocity is very small, and the red is going to indicate it's going to be high. So let me just show the movie. So you can see that the active particle comes from the left, it's going to the right, and it encountered that passive particle. Okay, and then it executed some some particular collision dynamics. So now how does one explain it? So we looked at this entire collision process in 3 different ways. In the first method, we sort of said that, that passive particle is just a point particle, and it does not, really affect the motion of the swimmer itself. So that is what we call as a tracer particle advection. Then we tried it using in a different way where you talk about the interaction, but in an analytical fashion. And that method is called method of reflection. If anybody is interested, I could explain more. And then we also do, lattice Boltzmann simulations, which means I'm gonna solve for the flow field completely. And the result was that we understand this entire collision as a 3-stage process. So in stage 1, you have the red particle, and this blue is now the passive particle. Basically, the blue particle gets attracted towards the red particle. So because the red, essentially when it moves, it generates a flow which will attract it. And as they come closer, the flow basically will be to repel this blue particle down. And then when the red particle, once it goes past, the swimmer goes past the passive particle, then the interaction is again going to be attractive. So actually there is an attraction, then there is a repulsion, and then there is an attraction. And you can see that this entire interaction process is simply mediated by the fact that this is happening in a fluid, and it's a fluid mediated interaction. So we call it hydrodynamic interaction between the particle. So just to tell you how interesting this interaction is, because the particles are different, the strength of interaction is also different. People who like to think about in terms of strength, you basically, what that means is that the swimmer sees the passive particle with a strength of order 1 by r square, where r is the different distance between the particle, while the passive particle or the colloidal particle would see the swimmer with a strength of order 1 by r to the power of 5. Okay, so then the result is that the active or the swimmer doesn't, so this is again a plot where the swimmer goes from left to right, and these trajectories that you're seeing, the red is the trajectory of the active particle or the swimmer, and the blue is the trajectory of the passive particle. And the origin of these three stages, so you can see that there is a left, something like that, then there is a repulsion stage and there is an attraction stage that really comes from this three-stage collision. Okay, so there is a three-stage hydrodynamic collision that happens. So this is a crowded slide, you can ignore everything except this part. Okay, I'm only explaining this. So here in this example, what we looked at is that if you have a series of such active particles that are going to come from left to right, then what would happen to that, that blue, the passive particle? And what we find is that if there are series of swimmers that are going to come from left to right, this passive particle after each collision will get further and further down and will move towards the channel wall. Okay, so that means that you are able to displace, let's say, a colloidal particle in a microchannel using the an active particle. And then of course, we have done quite a lot of studies based on how strong this, active particle should be and in what context it will move and so on. But this actually gives rise to a nice idea that needs to be tested, is that you can move a colloidal particle with with an active particle in a direction that you prefer. So that's the first part of the talk. So so these microswimmers actually exhibit quite a lot of interesting trajectories, which I didn't show, but I actually showed that you can move the passive particles in a desired way by using this active particles based on hydrodynamics alone. Okay, so that is the first piece of the work that I wanted to talk about. The second piece of the work is where I want to go on from a single active particle to suspension of active particles, which some of the examples that I showed in the beginning. Okay, so you have a dense suspension of, let's say, bacteria or cells or cellular extracts or of something of that sort. And then how do these things behave if I put it in a channel? Okay, so again, you can just look at this particular picture here. So what they have done is that they made an active fluid, again using the cellular extracts, and you have ATP present plenty. And what that means is that the fluid will continuously move. Okay, now what they found is that when they put this fluid in this microchannel, which is essentially a toroid, what happened is, what they observed is what you see here. Okay, you can see that the fluid was not static. The fluid is continuously moving. The fluid is actually moving in a counterclockwise fashion here. Now, the fact that it is moving continuously is not really surprising, because there is a continuous input of energy into the system through chemical reaction, and that's exactly manifested as a continuous motion. Now, to their surprise, they found that, yeah, this is actually moving continuously in the channel. Then what they did is that they took this toroid and then they basically reduced the height of the toroid. So when you have a fluid or any system and then you put it in a confinement, and what you expect is that the more you confine it, the more control you have on the system. That's what you typically expect. So similarly, when they reduce the height of this, toroid, they expected this flow to be much more smoother. But what they found is exactly opposite. That's what is shown at the figure here. You can see that the counterclockwise fluid flow that was there has completely disappeared. But instead, the flow looks more turbulent-like. Okay, so this was quite counterintuitive, and this is how active fluids behave in some sense, that they behave quite differently from the way we expect. So then the question was, could we explain it? Okay, so again, we sort of looked at it, using a bit of theory and computer simulations. So what we do is that we model these systems using the theory of liquid crystals. So for example, I don't know if people who have attended last month's this talk, there was a talk about what is a pneumatic liquid crystal and so on. So one could use a similar theory here. So what we did is that we said, okay, we will just prescribe what is really required to, to explain or to describe the fluid flow motion. In other words, we say that the fluid is, it conserves mass. The mass is not going to go anywhere. So that's what the first equation shows. The second equation is essentially Newton's second law, saying that, force is proportional to acceleration. And then we add an additional equation, and that additional equation is going to tell you how the structure of the fluid, the constituents in the fluid flow is going to change. So if it's bacteria, it could represent the orientation of the bacteria. If it's those filamental structure, it again would represent the the orientational order in the of the filamental structure. And what we say is that essentially it's going to get a pneumatic structure. So to see that what so if I write down equations in this form, this actually represents that of a passive pneumatic liquid crystal. So to make it active, what we prescribe is an additional stress into the system, okay, which is proportional to an order parameter. That's what is defined as Q. And what we find is that this additional stress has two consequences. One is that this additional stress create a pneumatic order in the system, meaning that the active particles are gonna order it themselves like a pneumatic in a liquid crystal, so that we could show using a linear stability analysis. And then we went on to do a full solution of these equations by putting this active pneumatic into a channel like this. So we, unlike the experiment, we have a rectangular channel here. You have length, width, and height, and we varied the width and the height systematically. And this is what we found. Okay, we find that the fluid takes 4 different flow states. The first is what we call as a unidirectional flow, meaning the fluid basically goes from left to right continuously, like in a very well ordered structure. The second one is what we call as an oscillatory flow. So you can see that the unidirectionality is really lost, but instead you start seeing some kind of an oscillation. So now the thing about this first and the second state is that there is a net flow from left to right. Now, if you go to the third state, what happens is that these wave-like structures actually grow, and they grow so much that they basically start turning around, forming these little vortices-like structure. Okay, this is known as dancing flow. So this kind of a flow was reported earlier in 2D, but we again could figure this out in 3D. So this is called a dancing flow. But the important thing is that there is no net flow from left to right. And for another case that we observed is more turbulent, like as you observed in the experiment. So what we found was that you are able to get a net flow versus no net flow. And we were able to actually see this by simply changing the cross-section of the channel. Okay, just like the way we saw it in the experiments. And if you're wondering why this is the case, the whole thing is essentially due to friction. Okay, so when the more you confine a system, so unlike the normal fluids where you will be applying some sort of an external pressure, or you will be moving a plate to move your fluid, here the source of the activity or the source of energy is distributed everywhere in the system. And the moment you start putting more and more constraint, the energy or the flow that is generated by the each sources get constrained by the friction. Okay, and therefore friction will stop any dissemination of information, and that's why you don't get a net flow when when you confine it more. The system looks more turbulent like. So that's the physics that emerges from doing these simulations. So the conclusion from the second part of my talk is that active fluids essentially behave in a very different fashion, and particularly the confinement has quite a lot of effect, which we call as the frictional effect is known as hydrodynamic screening. So both in the first part and in the second part, what I have shown is how do fluids behave in a very different way when you have active particles present in the system, and particularly in microchannels.
So we have consumed 20 minutes now. Okay.
Yeah. So so this two topics are in these journals if you would like to look like, and I would also like to thank my students and collaborators without which these works would not have been possible. So I have just one more slide, which is in the context of the series, is that the things that I showed you are essentially computational investigations, and some of them of course are inspired by experiments, but one could really think about doing a large number of experiments. And so I have divided this slide into two parts. On the left side I am talking about synthetic active systems. For example, if you're not a biologist but would still like to work with active systems, this is so there are two typical approaches. One is that you make a Janus particle, meaning let's say you take a polystyrene particle, coat it with platinum or any of the other catalyst, and you put it in a, let's say, hydrogen peroxide solution. And then the reactions will happen only on one side. That means immediately this particle will see a concentration difference on the two sides. And that concentration difference could manifest as an osmotic pressure, and the particle would start moving. So this movie that you're seeing here is essentially such a Janus particle. Okay. And this can be really thought about as an active particle, because the reaction, the source of motion or the source of energy is really again coming from an individual level. Or you could again think about these kind of systems where you have magnetic particles, and you spin the magnetic particles continuously applying in an applied magnetic field. And if the particle itself is anisotropic, such a spin could again move the particle. So here they put two spheres, made a doublet, and then made the particle to move, and so on. So these are the synthetic active particles, and you could ask a lot of questions like which of them essentially imitate the biological particles that we have seen. How do you sort of maintain the source of energy continuously as what happens in in the motion of cells and so on? What happens? So I showed you that the geometry has a very important role to play. So the moment you put these particles into various geometries, how are they going to respond? The moment you put many of them together, how do these things respond, and so on? So that's how you could ask a lot of questions. On the other hand, if you are interested in using actually biological systems, then again as I showed you, the importance of geometry is one big question that you have. You could look at a variety of organisms over a large length scale. It's also shown that even tissue development can be actually thought of as a flow. And what I have shown is that you could control such flow, which means that you may be able to even control the growth of tissue. You may be able to control the tumor growth, and so on. So there is a lot of avenue, for even biologists to think about controlling their systems, but purely from a physical point of view. So that brings me to the end of my talk, and I thank once again for the arrangement, as well as to the audience. So if you have any questions, I'd be happy to talk about it. Yeah, thanks.
Very nice, very nice. So let me just start with one question. So you talked about the first example, the colloidal particles can be pushed down in the course of flow. And that's very interesting to look at, say, something in the context of something that precipitation is a very important subject.
Right.
Whether it is in chemistry, whether it is in wastewater, or whatever, precipitation. So not only in microfluidics or any such thing, is it possible to think in terms of active motion induced precipitation, and can that be applied?
Yeah, I think it must be possible. So as you saw that the continuous interaction essentially can be utilized to direct the motion of the colloidal particle. Now, how exactly one could implement it in case of precipitation, I don't know at the moment, but I would say that considering that there could be an interaction and that could be a directed one, we must be probably able to think about ways of doing it. And so I don't know whether you remember one of the first example that I showed about where again you have a single particle, an active particle, which is collecting quite a lot of things around the active, passive particles around the active particle. So if you could even move, so you can think about probably making such clusters, and then you could think about moving these active particle in a desired way. That's another way of approaching it. But I believe it must be, it might be possible. We probably will have to think about how to sort of implement it so that you can achieve it as a precipitation.
In biology, are there examples? Are there natural examples of that?
So the natural example that I can think about, which people have explained, is the inside the cell. If you imagine that the cell itself is made up of lot of active particles and passive particles, then people have shown that the activity could lead to phase separation of active and passive particle. So the active particles actually come together, while the passive particle, move to a different place. So such phase separation is achievable, and people think that that may be one way in which cells is, organizing its structures. And you can explain the entire morphology of, actually not morphology, the inside, the heterogeneous nature or the pattern of the structure from activity. So that's one example that I could think about. Yeah.
Thank you. Pallab, you have a question.
Yeah, yes. Hello, sir. This was such a wonderful presentation. I just wanted to ask you a direct question about this work, which is also somewhat related to kind of work that I'm doing. So the question is it like, I have seen from your presentation that how particles would behave in a fluid, which is in a micro channel, right? Which is also flowing. So is it possible to calculate such particle trajectories, or precisely say something like where is that particular particle, not in a channel, but if I say in a liquid droplet, or to be precisely, if I say like, if you have a particle, like let's say a nano or microparticle in a nanoliter volume liquid droplet,
right,
which is also flowing, like moving, the liquid is also moving, the particle is also moving. So can you precisely say that where is that particle, whether it is at the core or somewhere between core and the periphery, or where is the trajectories like that?
Yeah. So we have looked at actually this problem of an active particle inside a droplet. The simulations that we have done so far and the investigations that we have done so far are all in 2 dimensions. And our investigation at least shows that it cannot be at the center, because if the moment you put it at the center, the structure seems unstable. So it's never going to be the case that the active particle is going to stay at the center of a droplet. But where does it go? We don't know yet, because we have trouble in simulating such systems when it reaches near the interface.
So right away, you have an experimental result here, which can be explained.
Yeah, so we have been trying to do this for a few years now. We find it extremely challenging to actually do this computationally, because you have multiple length scales, one coming from the interface, you have the flow, and then these particles basically bring in it's like a multi-phase problem. So you have a solid, a liquid, and a gas. So all of them doing simultaneously becomes a little challenging.
Yeah, just to let you know that why did I ask you this question is because this particle in a liquid droplet, or essentially molecules in a liquid droplets, are showing very interesting properties these days that people are looking at. And they show different chemistries, eventually way more different than the bulk, something people couldn't even expect. So and also there are certain theories that people say that these reactions are happening at the interface, not at the beneath the interface, or not at the core, or nowhere. So if we can somehow like locate the particle, whether it is at the interface or beneath the interface or at the core, they behave differently. Or if you have a mix of particle, like as you showed in your second presentation, that if you have a mix of particle, how do they behave? So if there's a way that we can say that this mixed up particle can be separated or aggregated, or whatever the phenomenon or chemistry they are doing, theoretically can be predict, and that's how the experimental result can be explained. That would be a very nice problem.
So I mean, I'd be very happy to look at that experimental literature that you are talking about. If you could just
he's talking about his own PhD problem.
Oh, I see. Okay.
And there are sort of interesting results that he is seeing, and that needs explanation.
I see. So
I
there are a few longer chat with you, Pallab, and then
there are a few papers in this area in the context of some PNAs and all to do with origin of life and aerosol chemistry, interesting micro droplet new science, biomolecular aggregation, many different subject areas. But that is all related to this probably these active particles in confinement.
Correct. Yeah, possibly. I think it's a new area and people are just exploring and, trying to sort of tabulate all the observations that you see at the moment. I think that's where we are.
Okay, right. Yeah. Are there other questions? Otherwise, we'll move on to the last talk. You appear to be a little older these days, Sumesh. Okay.
Can find at home. Yeah. Okay. Yeah. Carry on.
All right. Thank you. And Esma. We were supposed to have a talk by Ramesh Gardas, our faculty colleague at chemistry. He could not do so. He will probably come in, and then I took the suggestion of our colleagues that why not we have a student giving a talk. Now this person who is giving a talk is not now a student. She graduated. She's Dr. Esma Khatun. Go ahead, please share.
Good evening, everyone. So let me share my screen. So is it visible?
Yeah, it is, and not full screen yet.
Yes, sir. Now is it full screen?
Yeah, go ahead.
Yeah. A very good evening to one and all. Myself, Esma Khatun. I have completed my PhD degree under Professor Pradeep. Today, I will be talking about atomically precise alloy nanoclusters. So, nanoclusters are the special types of nanoparticles which are composed of precise number of atoms, and their size fall in between 0.1 to 2 nanometer. They are stabilized by various kind of ligands such as DNA, RNA, protein, peptide, thiol, phosphine, etc. And they are represented by the number of metal atoms and ligand molecules present, such as AU25 ligand 18, Ag44 ligand 30, etc. Due to their smaller size and precise atomicity, they exhibit quantized energy states which give rise to molecule-like optical features, as shown here. So other interesting properties exhibited by nanoclusters are exciting luminescent properties, chirality, magnetism, and good catalytic activity. So these properties broaden the range of applications of nanocluster in various fields such as biomedical applications, sensing and catalysis, and in energy storage. So controlling these nanoclusters with atomic precision is not an easy task. However, researchers have developed many synthetic procedures to make stable nanoclusters, as shown in this figure. And among all these nanoclusters, the most studied one is AU25 ligand 18, and here it is the well-defined absorption spectrum of AU25, which shows three distinct absorption features, and this is the X-ray crystal structure of AU25. The nanoclusters can be precisely characterized and their composition can be unambiguously assigned by using mass spectrometry. And here is the ESI MS of AU25 ligand PET18, AG25 DMBT18, and AG29 BDT12. So to assign the composition, the well resolved isotopic distribution, as we can see here, is matched with the calculated one. And here we can see that the calculated isotopic distribution pattern of AU25, AG25, AG29 exactly matched to that of experimental one. So this confirms their composition. Though mass spectrometry can give us the complete composition of nanocluster, but the structural details cannot be obtained from mass spectrometry. So for that, we need single crystal to diffract it and get the single crystal structure. So most of the nanoclusters consist of a metal core which is stabilized by an outer staple made up of metal and ligands. And these metal cores can be of can be single crystalline, such as FCC, BCC, or HCP, etc. And it can also be icosahedral, bi-icosahedral, and decahedral structure. Similarly, the outer staple can be monomeric, dimeric, or polymeric. In this metal core and metal ligand staple, if we replace one metal atom with foreign metal atoms to make alloy, it can affect their structure and properties greatly. So alloying in gold and silver nanoclusters usually show significant effects on their stability, luminescence properties, and catalytic activities, and so on. Hence, it is of high importance to tailor to make alloy nanocluster for tailoring their properties and broadening their applications. So during the doping to make alloy nanoclusters, there are various doping sites, and depending on the foreign metal atoms and synthetic procedures, these doping sites can be changed. As we can see here, platinum, palladium, nickel mostly prefers to occupy the central position. However, the copper atom mainly prefers the outer staple, and silver and gold atoms can occupy any possible positions. So so by proper combinations, more than one metal atom can be incorporated to make multi-component alloy nanoclusters, such as trimetallic, tetrametallic, and so on. So as silver doping in gold nanocluster is of interest because atomic radii of gold and silver are nearly identical. So in order to understand the effect of silver doping in gold nanoclusters, Kumara et al. Have synthesized gold-silver alloy nanoclusters by co-reduction synthetic method. Here they observed the formation of more than 7 silver doped gold AU25 nanocluster, and they have assigned this via ESI MS. Also, they have crystallized it, and the single crystal excess structure showed that the silver atoms occupy the icosahedral surface positions. Another 25 atom gold silver alloy nanoclusters co-protected by thiol and phosphine ligands was synthesized by ligand exchange method. Here doping of maximum 12 gold silver atom were observed. Surprisingly, the luminescence intensity enhanced the luminescence intensity enhanced 200 folds upon doping of 12th silver upon doping of the 12 silver atoms. And this enhanced red luminescent cluster was further used in the bioimaging. So similarly, the doping of gold in silver nanocluster is also interesting. Mostly, the doping of gold enhance the stability of silver nanoclusters. One such example is shown here. The silver 17 ligand 12 cluster was assigned using ESIMS, although due to its lowest poor stability, single crystal was not obtained. But when once gold atom was doped and to make AG16 nanocluster, this nanocluster stability enhanced, and we can get single crystal out of it. So not only the stability, but the emission property can be improved by this doping. So here we can see the gold doping enhanced the gold doping in silver 29 nanocluster enhanced the luminescence intensity, and this the structure of this nanocluster, one gold dope nanocluster was obtained. However, other structure was calculated by DFT calculations. So similar to gold and silver, copper is also in the same period, same group of the group in the periodic table, and copper gold and copper silver bond is stronger than gold and silver bond. Thus, the doping effect of doping of copper atom is important to know. So here, such an example is like doping of copper atom in gold 38 nanocluster. So here they have observed the doping of copper around 7 copper atom in the staple positions. However, this doping doesn't change their absorption spectra much. So that means like due to the copper doping, there is no such change in the electronic electronic structure of the nanocluster. So also copper doping can induce some interesting chiral property in a nanocluster, such as here they have synthesized, authors have synthesized silver 28 copper 12 nanocluster, and this nanocluster was shown showing intrinsic chiral property is due to the formation of chiral core. So other than copper, silver, and gold, this platinum, palladium, nickel were also doped in gold and silver nanoclusters, and said that platinum, palladium, nickel prefers to occupy the central position. So here is the crystal structure of platinum Au24, where platinum atoms occupy the central position, and due to the platinum doping, the yellow color Au25 solution turned into green color solution. So that means the doping of platinum significantly affect the electronic structure of nanocluster, and also this platinum doping induce the catalytic activity of these nanoclusters. This platinum Au24 nanocluster was successfully used in hydrogen reaction. Also here it is shown, also here the authors have shown that the catalytic activity of palladium doped Au24 is towards the conversion in benzyl alcohol oxidation is higher than that of monometallic Au25. In the case of Ag25, also we can observe this kind of doping of platinum, palladium, and nickel, and also this kind of monodoped silver 25 nanocluster showed higher catalytic activity towards the carboxylation reaction of CO2 with terminal alkyne through CC bond formation to produce propylic acid. their catalytic activity is higher than the monometallic analog Ag25. So also we have observed the doping of cadmium and mercury in gold and silver nanocluster. Though doping of cadmium and mercury is a bit difficult, however, it was obtained and the doping of cadmium in gold nanocluster can only be obtained via anti-galvanic reduction process. Here, cadmium thiolate was added to the silver 25 nanocluster, and then one single cadmium doped alloy nanocluster was obtained. The cadmium atoms was observed to occupy the central position as shown by their revealed by their single crystal X-ray structure. This kind of nanocluster can be useful for some NIR application, because this kind of nanocluster shows some NIR luminescence. Also, in the case of silver nanocluster, we have observed that doping of 12 cadmium, and here also the NIR luminescence was observed. So recently, ruthenium atom was doped in gold nanocluster, and as we know, ruthenium is can have magnetic properties. So this nanocluster can show some magnetic properties. Also this shows this work shows the opportunity to synthesize many other nanoclusters in silver and copper also. So from our lab, we have obtained the doping of iridium in gold nanocluster. Here, 3 iridium atom was doped in gold nanocluster via intercluster reaction. Here, the reaction between Au25 and iridium 9 thiol 6 nanocluster was performed, and this intercluster reaction showed the incorporation of 3 iridium. And this iridium doped nanocluster can be can be used as future magnetic material. So intercluster reaction is a very good method to synthesize alloy nanocluster, and this was first observed in our lab. One of our senior, Krishnadas, has first observed this intercluster reaction between Au25 and Ag44, and this result in the formation of bimetallic gold doped Ag44 and silver doped Au25 nanoclusters. So in order to extrapolate this intercluster reaction, I have synthesized, I have done the intercluster reaction between one bimetallic Ag28 nanocluster and one monometallic Au25 nanocluster, and this led to the formation of a trimetallic nanocluster. So for this intercluster reaction, first I have synthesized the bimetallic Ag28 nanocluster, and for that I have first synthesized platinum, palladium, and nickel doped Ag25 nanocluster via co-reduction method, and then by adding BDT and PPS3, which lead to the ligand-induced structural transformation to form platinum, palladium, and nickel doped Ag28 nanocluster. So then these Ag28 nanoclusters were reacted with Au25. Here is the reaction between palladium Ag28 and Au25 is shown. The reaction was monitored via the time-dependent ESI-MS, and the ESI mass spectrum of each time interval is shown here. Here we can see that as the time increases, the number of gold doping enhances, and after 24 hours we can obtain 12 gold doped palladium Ag28 trimetallic nanocluster, and on the other hand we can see the silver doped doping in Au25 to make several bimetallic nanoclusters. Similarly, we can see similar kind of reaction between platinum Ag28 and Au25 nanocluster to form the stable trimetallic platinum Au12 Ag16 nanocluster. So to understand the reaction mechanism, we thoroughly done the reaction between Ag29 and Au25 nanoclusters. Here we have observed that similar to palladium and platinum, only 12 gold doped 12 gold doping was observed here. However, if we see the structure of Ag29 nanocluster, there we have Ag13 icosahedral core and which is stabilized by Ag16 outer staple motif. And so if gold doping happens via the core, then we should obtain the 13 gold doped, but here we get only 12, maximum 12 gold doped. From there, we proposed the reaction mechanism that the gold atom of Au25 nanocluster is not directly interacting with the silver atom in the core. Instead, they are interacting with the silver atom which are in the staple, and then it is the silver atoms are getting replaced by gold atoms. Then via the thermodynamically stable via the intramolecular galvanic reduction, thermodynamically stable structures gets formed where gold atoms occupy the surface of icosahedra. So similarly, we have synthesized several multimetallic alloy nanoclusters via anti-galvanic exchange and intercluster reaction. For anti-galvanic exchange, we have added copper salt in monometallic Ag29 nanocluster to make bimetallic copper doped silver 28 nanoclusters. And also, similarly, we have obtained the trimetallic platinum copper doped platinum Ag28 and trimetallic copper doped Au12 Ag17 nanocluster and tetrametallic nanocluster platinum Au12 copper 4 and silver 16 silver 12 nanocluster. So also, we have observed that this alloy nanocluster can be formed by intercluster reaction. Here we have reacted, instead of using a copper salt, we have used a copper nanocluster. And here we observe the doping of copper atom is higher than the anti-galvanic exchange. Here we observed only maximum 4 copper doping, where in the case of intercluster reaction, we observed more than 8 copper atoms, more than 14 copper atoms.
You have used 22 minutes.
Okay. So this, the reason behind this has to be analyzed by theoretical study. It is maybe there, maybe there are some maybe there are some interaction in the transition state, so that need to be calculated. So now coming to the connection between theory and experiment. So till now I have talked about various mono and multimetallic nanoclusters, and many of them have single crystal structure, but most of them do not have single crystal structure, mainly for these trimetallic and tetrametallic nanoclusters. So we need to, for understanding this structure and their properties, we need the help of theoretical study. So one such example, like we have shown here, like we have obtained the structure of palladium Ag28 by the DFT study, and by the TDDFT we have computed the absorption spectra, and we have matched it with the experimental one, and we have compared the energy of various isomer, and the most stable isomer has been chosen as the as the most favorable probable structure. So also this theoretical study can be used to understand the emission property of this nanocluster. One such example is shown here. Previously, I have talked about the luminescence enhancement due to gold doping in Ag29 nanocluster. Here they have shown the origin of this photoluminescence enhancement. And also using this theory, we can study the energetics of the exchange reaction, this intercluster through the intercluster reaction. Here one such example is like exchange reaction between Ag25 and Au25, and here the calculation showed that this reaction happens because this goes through the exothermic exothermic process. So in the future, what we can do in respect of experiment, like we can synthesize more trimetallic and trimetallic nanoclusters, and we can incorporate more than like 5 or 6 nanoclusters, which can lead to the synthesis of high entropy alloy nanoclusters. Also, we can dope iron, cobalt, and various lanthanides. It can induce the magnetism and other photophysical properties. And also we can study some circularly polarized luminescence, magnetofluorescence, etc. And the study of ligand dynamics can be studied during the intercluster reaction, and the intermediates can be trapped, although this need a detailed computational support. And also the supramolecular assemblies can be formed that will help to the applications of alloy nanoclusters. So finally, I would like to thank my guide, Professor T. Pradeep, and my colleagues, collaborators for my work, and my friends and family. Thank you. And thank you for giving me this opportunity.
Well, let us take questions if you have. There are questions.
Yeah, hi, good evening, everyone. I'm Shiv Shankar. So
Hello.
I have, yeah. So such a nice presentation. I have a very small fundamental question. So you are talking about cluster. So this is very small size. So due to small size, there is a high chances of agglomeration. So how did you avoid that agglomeration of the clusters?
These clusters agglomeration means in solution?
Yeah, coming together and form a bigger cluster.
Actually, these nanoclusters are stabilized by various kind of protective ligands, which restricts this kind of agglomeration. So this is like these are not like if we keep it in some iron bin, then it can agglomerate. Otherwise, these are individual entities.
So otherwise it is means you are using some solvent and something to stabilize it, or it is already stable?
It is stabilized by using some protective ligands, and these are stable.
Okay.
These
What
are,
is that?
yeah.
What is that ligand for silver?
So actually, as I mentioned previously, like various types of ligands are used, like DNA, RNA, protein, peptides, thiols, phosphine, and nowadays, like in our group, carbonate thiols are also using to stabilize this kind of nanocluster.
Okay.
And these are highly monodispersed in nature, and they are not agglomerate.
Okay. Thank you.
Pradeep, may I quickly?
Yeah, go ahead, please.
Hey, Esma, nice
Yes,
work, good presentation as usual. I know all of your work though. I just need to ask you a few quick clarification. So these molecules, if you are asked to make in quantities, do you think you can make them if you find them a good property or so?
Like this, as I showed you, like this AG44 nanocluster now, till now, AG44, AU25, these nanoclusters were synthesized in bulk. So there are many such AG29 also. There are many nanocluster, and depending on their stability, they can be synthesized in bulk amount.
I'm asking whether you can synthesize, not can.
Yeah. I can synthesize silver 44, silver 29, and gold 25 nanoclusters.
You think you can make in quantities that could be utilized for some application if you can give it to others?
Yes.
Okay.
We are giving about a gram.
Yeah.
Wow. Wow. Nice. Very nice work, Esma. Congratulations.
Thank you, sir.
Sanjeev here. Can I have a question?
Yes, sir.
Esma,
Yes,
so
sir.
my question is there a rule which you follow that, okay, I'm looking for this particular property and this could be my dope and this should be my parent nanocluster, and if I take A and B, then I get C, which could have this particular property. Is this a rule which you follow, or it is more like a random try and then get something and characterize it?
Sir, actually, there is no such rule, but certainly, like if we want magnetic property, like I was telling, then we will use that kind of metals like ruthenium, iridium, and nickel. And if we want some luminescence property, then like as we know that as the size gets smaller and smaller, then luminescence property enhances. So we will try to use those kind of ligands which are known to form smaller nanocluster mainly, to make although then exact precisely we can't synthesize, like we want 13, so we will get 13, maybe we can end it up to get 20 or 25 like this, so
That
we
means
can
many a times it had happened that your product is not thermodynamically stable, right?
yes, sir.
One more thing I just missed, how did you propose the mechanism? You showed some NMR perhaps, the data where you had time evolution of the changes, right?
Sir, in this reaction here,
Yes, yeah, right, this one.
yeah, here actually this AG20 silver 29 and gold 25 we have reacted. So silver 29 is has a silver 13 icosahedral core. So if the AU25 atoms are directly interacting with the core, like as I mentioned previously, like a nanocluster is having one metal core which is stabilized by a outer staple made up of metal and ligands. So if it is interacting directly with the core silver atoms, then this 13 13 silver atoms should be replaced by gold atoms, not only only 12. So as it is 12, like we can see here, like 12 this staple is there, like AU3 SR3 staple. So through via this staple, if it is interacting, then only 12 gold can be doped, and this that inner metal atom that can be intact. That, and also when we used the central doped Ag29 nanocluster, like platinum palladium doped, so platinum palladium will occupy this position. So if there is a interaction directly with the AU25, then the platinum will also come out, and that will also get doped in AU25, and
It's
that
also
will
knowledge
also
based.
yeah, but we are not getting any such product.
Yeah, okay, I got it. Thanks.
Thank you, sir.
All right. Okay. I don't see any other question. If there are any, please go ahead. Otherwise, we are going to close this meeting. In case you again wish to make a presentation in this, please send a mail. And we will meet next month in the 3rd week, and schedule will come to you very soon. Thank you very much.
Thanks, Pradeep.
Good night. Good night. Yeah, thank you.
Bye. Thank you.
Thanks, Pradeep. Thanks a lot.